the concept once again. Ganesh, can you see this PPT?
Yes, sir.
Yeah, just listen it like a story. I have made a interpretation of frequency domain analysis with some of the signals and system concept. Okay, so if you are able to understand, that is fine. If you are not able to understand, that is also fine. So how we can write block diagram representation for uh, the input signal and the output signal for a linear time invariant continuous time system, CTLTI. Continuous time, linear time invariant system. I hope everyone is aware what is continuous time, what is linear, what is time invariant by now. So whatever analysis we are doing in a control system, okay, for the entire course, it's only about continuous time, linear time invariant system. So where x of t is the input signal, y of t is the output signal. So instead of g of s, now I'm replacing my system representation with h of t. That's the only difference. H of t in signals and system terminology, you had called it as impulse response of the system. Whereas even in control system, G of S is called as impulse response of the system. Why it is called as impulse response of the system? The transfer function, which we understood as a ratio of Laplace of output by Laplace of input, is also called as impulse response of the system. So what is meant by that? So we knew that C of S by R of S equal to some transfer function G of S. C of S by R of S equal to some transfer function G of S. So if I rearrange C of S equal to G of S into R of S, R of S, so C of S is nothing but Laplace of the output. So C of S equal to G of S only when R of S is unity. Okay, only when R of S is unity, where this R of S is equal to unity only for the impulse function. So Laplace of impulse function is unity. Therefore, our output is equal to g of s transfer function when I apply impulse signal. That's why we call the transfer function as the response of the system for impulse function or impulse response of the system. So similar thing is true even in signals and system. Then they have defined that it should be absolutely integrable. So that's what is meant by continuity or continuous time, and it is given by integration over a range for the magnitude of h of t should be integrable and it should have a finite value. So this is also indirect way of representing the bounded output or the system stability over a range of time. Okay. Then the response of the system to a sinusoidal input. So what will be y of t when x of t is equal to some signal which is having a frequency and some phase angle theta. Okay. So the time is subset of a real values. So cos and sine both represent a sinusoidal signal. So we start by looking for the response yc of t for the same system xc of t. So next, let me consider another way of representing a sinusoidal input with this expression. And I want to find the output for this input, not for this. So how mathematically we can write? So this is how where the convolution appears. The output is obtained through convolution. But what we did in the control system is we multiplied g of s with the r of s to get the output. We didn't do the convolution. So convolution should be done when we operate with the time domain signals or when we operate in time domain. So in time domain, we cannot directly multiply the transfer function with the input signal. This proof I think you have already done. If not, you might be doing this. Okay. So yc of t is h of t, which is transfer function in control system in time domain, convolved with xc of t. If I write this in Laplace, it is yc of s equal to h of s into xc of s. Fine. So next, proceeding with convolution, this all stuff you already know. So convolution of h of tau, xc of t minus tau d tau. This is basic convolution expressions. Then I will rewrite xc of t minus tau as e raised to j omega naught t minus tau into d tau. So h of tau remaining as it is. So it's convolved with over a range. Then since this is integrated with respect to tau, I will take out e raised to j omega naught t outside, which is nothing but xc of t. Okay, the input signal. Then I have to multiply only with h of 2 e raised to j omega naught tau. Fine. So in the next step, I will replace that, and it goes like this. Then I will define uh, h of omega. Okay. So here is where we are encountering the frequency response, where h of omega is the frequency response of continuous time LTI system, is equal to Fourier transform of h of t. So this is a very, very important key point. Now I'm replacing, now I'm defining the frequency response for h of omega, h of tau as h of omega equal to. So what is the intention of defining that is, I want to do some modification at this point. So for that I define the frequency response of continuous system, LTI system, which is also equal to the Fourier transform of h of t. So please do remember this slide, guys. This is very important. So once I replace, I will go with the multiplication. Okay. So yc of t equal to h of omega naught xc of t. Fine. So xc of t is nothing but e raised to j omega naught t. So therefore, the response of LTI system to a complex exponential is another complex exponential with the same frequency omega naught. Okay, omega naught, but h of omega naught will contribute two other additional features, which is in terms of magnitude and phase angle. Fine. So yc of t is something multiplied with a complex exponential. Our input was complex exponential. So finally, we can conclude our output is something multiplied with complex exponential. That something is h of omega naught here, which adds the magnitude part as well as the phase angle part. This e raised to j arg h of omega naught is nothing but the phase angle added by this particular term. That is because of h of t. So we call it as output signal's magnitude, that is magnitude of IC of t. Then this particular term represents the phase angle of output signal. Okay. So going a little in depth, now I am actually representing my sinusoidal signal as a combination of exponentials. This we have already done in complex theory, complex number theory. We can represent cos omega naught t plus theta in terms of exponential like this. Okay, so that is e raised to j5 plus e raised to minus j5, something like that, divided by 2. Fine. So e raised to j theta. Theta is the phase angle which is constant, but j omega naught is something related to frequency, which will keep on varying. Okay, which will keep on varying. Or if you have something like Fourier transform of some signal, then this omega naught will definitely get introduced in that expression. So I will rearrange all this thing, and now I will take the response of the system for x of t, which has two exponential terms now. Fine, which has two exponential terms. Therefore, I can directly write from the previous results that 1 by e raised to j theta, which is constant here, and e raised to j omega naught is something like this, will keep as same. Yeah, it was same as the previous one. Yeah, e raised to j omega naught is same, but only h of omega naught is getting introduced here, which is the frequency response of h of t, or Fourier transform of h of t. And since we have a negative sign here for the second exponential term, so we will have h of minus omega naught. Fine. So you can ask me a question, what is meant by negative frequency? Why it should be minus omega naught? Okay. So this question is answered in a spectrum plot of a given signal. So if you do remember a spectrum plot of a signal in your Fourier transform, that we take a 0 radians per second or 0 hertz as a reference point, and with respect to that, if you plot the spectrum of a say square pulse, one square pulse, you will end up with some um, what I can say, symmetrical plot over negative and positive frequency range. Okay. So in practical, we never apply a negative frequency, but it is only for a theoretical understanding of the distribution of the spectrum, only for the theoretical understanding of the distribution of the spectrum. Fine. Next, continuing with that, if h of t is real, then h of minus omega is h star omega, which we can say that this is positive. Okay. Then how do you get your magnitude and phase angle is something like this. Okay, magnitude is like this and phase angle is given by this term. And for negative real value, I have already said we will have a negative phase angle. So this phase angle goes with respect to the axis on the complex plane. So if you have a real value positive and imaginary value as positive, your phase angle will lie in the first quadrant. And if your real value is negative but imaginary value is positive, your phase angle will lie in the second quadrant. So with that concept, the phase angle for this term is represented. So finally, what we can conclude is the output is given by both magnitude of h omega naught, h of omega naught, and the phase angle contributed by h of omega naught, plus the magnitude of h of omega naught and the phase angle contributed by h of omega naught. Okay. So this something catchy here. What is meant by if h of t is real? So if h of t is real, it is same as asking question whether your g of s is real. Okay, whether your g of s is real. So if you think practically, our g of s can never go imaginary. Okay, our g of s is always real only. Fine. So it will never go as something different from the real. Therefore, this final expression is valid for all our practical systems. That is, output of the system when you apply a sinusoidal input is or will have a same frequency but different magnitude and a different phase angle. Okay, omega naught defines the frequency of the output, and this argument h of omega naught is the phase angle contributed by our transfer function. Fine. So I don't want to confuse you further. This is final expression. So therefore, the response of the system for an input x of t equal to some sinusoidal signal with the amplitude of a is equal to is equal to a multiplied with the magnitude of the transfer function at that particular frequency. Okay, so this term together represents the amplitude for the output signal. Now it can be a but not always a. Okay, and then the phase angle is this. Here he has written plus argument h of omega naught, but in general it can be plus or minus argument h of omega naught. Okay. So which is also sinusoid. So output is also sinusoid with the same frequency omega naught, but with amplitude scaled by a factor h of omega naught, and with the phase shifted by amount of ARG h of omega naught. Right. So that's it, guys. This is a in respect. I mean, in the interpretation with respect to your S and S concept. Fine. So here I have something more which will not be understandable by PPT. Instead of that, I will go with my handwritten explanation. Anybody understood? Anybody understood? Can say yes.
Understood, sir, but it's quite difficult to follow in the PPT. So handwritten videos were a lot better, sir. That's what I feel.
Handwritten is better, but handwritten is not necessary. That is story I told. It's not there for syllabus. Whatever I explained till now about frequency response is not there for the syllabus. At least you have understood the story, right?
Yes, sir.
So you, at the back end of your mind, you assume that there is a proof for that.
Okay, sir. No problem.
See, these things, no, these proofs and all, they are very complicated. Like at your level, it is difficult to derive on your own. But somewhere, the method what I have explained will be helpful while answering some questions or interview questions. So somebody may directly ask you, y of t equal to h of t convolved with x of t. Which is easier? Is it easier to calculate using convolution, or it is it easier using the transform? Okay, so one can say using the transforms it is easy. So what we do in transform, the Laplace transform specifically. So we write y of t equal to h of t convolved with x of t. The same expression in Laplace transform will become y of s equal to h of s into x of s, which is same as c of s equal to g of s into r of s. Fine. So under such scenario, you can use this knowledge and you can try to calculate. Okay. You can revisit this particular video and you can get more information by searching in Google, or any engineering mathematics textbook is fine. Fine. Any queries? Anybody has any doubts? Abdul Bakar, did you follow?
Yes, sir.
See, those who are not able to follow this, don't be under the impression that sir has explained everything very quickly, fastly. It's out of syllabus. I am actually giving additional knowledge for those who want to explore further or correlate the subjects, and some introduction to deeper mathematics. Those who haven't understood, please not worry at all. You can follow from this explanation onwards. Okay. And no textbook also will explain, no control system textbook will explain you how the mathematics, or how important the mathematics is. Every textbook, whatever I have read reference or something, have explained only from the point of control system. But control system is having a base in signals and system. So everything we operate in practical control theory is signal only, right? Signal input is given, signal output is obtained. Anything can be represented in terms of signal. But only additional thing is our transfer function, which is h of t in your signals, and here it is g of s. So we are adding a dynamics in our analysis. So that's what makes the difference between signal theory and control theory. But basically the mathematics of both will remain same, and these techniques are very much useful in like communication applications, and even in defense applications, so where you need to decode or decompose our radar signals and all. Then this knowledge is very much essential, both signal theory as well as control theory. Okay, so to move further, Ganesh, can you see this video?
No, sir.
Okay, okay, fine. So what we do now is we start with our actual syllabus. Before starting this, one key point you remember is that whenever a sinusoidal input is applied, you will get the sinusoidal output. Whenever a sinusoidal input of a particular frequency and amplitude is applied to a dynamic system such as RLC circuit, then your output is also a sinusoidal function, but with a different magnitude and different phase angle. So if you are able to understand this from the previous explanation, that is sufficient. So keep this in mind. So what we'll do now is we proceed with our actual syllabus. So how do we define frequency response? Is response of the system for sinusoidal input at different frequencies. And one additional condition is that it is in steady state. So the frequency analysis is done in steady state. So we saw in the previous class that frequency response equal to two terms, in which the first term was transient state or the transient behavior, which had e raised to minus t into some constant. And the second term was related to steady state. So transient behavior ended equal to 0 as t tends to infinity. So what remains at the end is only the steady state behavior. So frequency response is equal to steady state behavior. So this is a complete definition. Fine. So you should remember this. This is a sure short question in any interviews. Any interviews, first question they will ask what is frequency response. If you tell the answer without the word steady state, it is incomplete. Interviews in the sense, I am not telling that Wipro will ask this question. Some relevant core companies. This we have already proved in mathematical in the previous class. So now let us see. So now let us see how to analyze the behavior of the system for different frequencies. What is meant by analyzing the behavior at different frequencies? So we are already aware that input is sinusoidal. Let me consider a system, dynamical system, whose transfer function is g of s, which is similar to RLC circuit. Okay. So if you derive a transfer function for RLC, you imagine that it is g of s. So I am applying an input signal, okay, V in to this system. Fine. So what will be my output? So let me take input as 1 hertz, 1 hertz, and it has some fixed amplitude. So my output may go like this. Okay, may go like this. This is just approximate plot. So let me take the voltage across resistance as output. Okay, voltage across resistance as output. So since sinusoidal input is applied, voltage across the resistance is also sinusoidal, and it will have same frequency. So what is the difference? We can observe there is a phase shift and there is a change in magnitude. So let me take the input magnitude as 5 volt and output magnitude as 3 volt. Okay. So how do I characterize this behavior graphically? How do I characterize this behavior graphically? So before proceeding, let us just briefly revisit time domain analysis. In the time domain analysis, what we did is we obtained the time domain expression for output C of t and we plotted it on a graph where x-axis was time and y-axis was C of t output. So for every time we found out C of t, then we marked each point on the graph, then we joined all those points, which gave us the time domain analysis. A similar approach involves here also, but it's very much different from time domain case. So our axis now is the frequency in omega or f. Okay, frequency radians per second or hertz. You can take it in any way. And the y-axis will have something called gain, that is output by input, and another axis will have phase angle. Another axis will have phase angle. So instead of 1, now we have 2. We have 2. We should draw both. So how the x-axis values are written? Okay, it is on log scale. The x-axis values are written in a log scale, logarithmic scale. Okay, so logarithmic scale is something different from our conventional graph. So if you take 0.1 hertz here, then exactly after 10 points, you will have to take 1 hertz, then you have to take 10 hertz, then you have to take 100 hertz. So let me show you a graph of logarithmic scale. Give me one moment. Yeah, here is the example of logarithmic scale. Fine. This is much different from your conventional scale. So after 10 raised to 1, 10 raised to 0, so 10 raised to 0 is 1 hertz. So after 1 hertz, 2 hertz, 3 hertz, 4 hertz, 5, 6, 7, 8, 9, 10. 10 raised to 1 is 10 hertz. So after 10 hertz, we have to count as 20, 30, 40, 50, 60, 70, 80, 90, 100. 10 raised to 200, then 100, 200, 300, like that up to 1000. Fine. So this is the logarithmic scale. So we will be using the logarithmic scale for that. So let me write the gain for 1 hertz as say V out by Vi equal to 3 divided by 5 or 0.6, and phase angle, let me take phase angle as 30 degree approximately. So no calculation is done here. Just for the sake of how to plot the graph, I am showing it. So let me find mark the scale on y-axis. So mark the scale on y-axis for both gain and phase angle. This is again conventional, no strict rule that you have to follow this only. So I mark the gain as well as the phase. So at 1 hertz, approximately mark 0.6 and a phase angle of plus 30 degree. Plus 30 degree. Now let me change the frequency of the input to 5 hertz. This is a 5 hertz sinusoidal applied to the same system. So now again obviously there will be change in the phase angle as well as magnitude. So let me take now the output magnitude as 4 volt and phase angle, let me assume it as minus 10 degrees with reference to the input. This is always compared with respect to input. So now gain is V out by Vi, 4 volt, 5 volt. Okay, I have taken 5 volt as reference. So 4 by 5 is 0.8. So at 5 hertz, let me mark 0.8. And the phase angle I considered as minus 10 degrees. At 5 hertz, you should mark minus 10 degrees. So now join these points. And let me take another last example. So it has input same magnitude. Always it is same magnitude, only change in frequency. So now let me take the output. Sorry for that. Yeah. So the third output goes something like this. Now let me assume output as 4.9 volts for 10 hertz and phase angle as minus 30 degree. So what will be my gain? It is 4.9 by 5, which is approximately equal to 0.95 approximately. And 5 phase angle is minus 30. So let me mark 0.95 at 10 hertz. And similarly, let me mark this on the phase angle. So I have joined all the magnitude and phase angle for different frequencies. So if you plot over a range of frequencies, this is how you can expect. Maybe this may look like this. Okay, graph may look like this. Okay, phase plot and gain plot. So these are the two plots we get for a frequency response analysis. So what's the conclusion is you don't have only one graph, but you have both phase plot and gain plot. Which characterizes the behavior of the system in frequency domain analysis. So there is no single graph now, there are two separate graphs, unlike time domain analysis. So what is the typical plot for RLC circuit? Let me show you. Typical plot for, the frequency domain plot for RLC circuit. So you have a signal generator connected as input, for which you can fix the input voltage and vary the frequency, And if you go on varying the frequency and go on measuring the magnitude and phase, this is how you can join all the points. And the peak is called as resonant frequency, either in hertz or radians per second. And this is your phase angle plot. So at resonant frequency, there won't be any phase angle shift. So the peak depicts highest voltage developed across the resistance. It's not the value, but it's just the gain. Highest voltage drop across R, or the maximum current flowing in the circuit. It's an indication. It's not the exact value of the VR. Fine. Any queries, you can stop me, or else we will proceed further. Okay. So what is the next thing? So next question is, what are the key features that we can extract from the above graph? That we can extract from the above graph. So those key features are called as frequency domain specifications. Frequency domain specifications. So just by observation, you can name two frequency domain specifications very quickly. Very quickly. So can anybody has the answer for this? So one key feature is the highest peak. Highest peak is a kind of a specification we want to know. So what we call it? We call it as a resonant peak. The technical term for that is resonant peak. Symbol is MR. So this is MR that everyone wants to know. The designer wants to know. And the resonant frequency is also a key feature that customer will give us, and you have to design for that. So there are two more additional features. First one is bandwidth, and the last one is cutoff rate. Anybody has any query? प्रेम सिंह राठौड़, कुछ पूछना है क्या भाई? Okay. No question.
Sir, can you explain this on bandwidth and cutoff?
Yeah, that's what we are going to study now. We'll go one by one, okay? Bandwidth and cutoff rate, everything I will explain. I will not skip anything. Don't worry. Fine. I think nobody has a question. So let us find the theoretical expression as well as a conceptual understanding of these specifications. But the condition is, again, we are restricting this analysis to a standard second order system. That is, we are going to find the specifications for only this system. Our best friend second order system. Omega n square plus s square plus 2 zeta omega n s plus omega n square. So how are we going to derive these expressions using the second order system? So before that, we need to do some modification, mathematical modification. That is, we need to separate out the magnitude and phase angle part from this expression. Then only we are getting into derivation. Then only we can proceed. Okay. So we need to separate out magnitude and phase angle expression for expression 1. So now the question is, if you just look at this expression, it is like confusing. How you are going to separate out? How we can make a phase angle and magnitude? Phase angle and magnitude is only possible if there is a J term here, right? If there is a J term, but there is no J term here. Okay. So for these questions, let me answer. So we should write the expression 1 in this form. C of s by R of s, magnitude as well as phase angle, which is nothing but V out by Vi magnitude and V out by Vi phase angle. This we call as gain or magnitude both. and we can call this as phase angle. So here our V out was VR, voltage across resistance. So how to separate out magnitude and phase angle is substitute S equal to J omega. Substitute S equal to J omega. So many people substitute S equal to J omega. Many textbook will suggest to substitute S equal to J omega, but rarely no textbook has explained why we need to substitute S equal to J omega while separating magnitude and phase angle. So when you substitute S equal to J omega, we did this substitution in root locus, if anybody can remember. We did this substitution because we wanted to find the point of intersection of root locus on the imaginary axis. Okay. So that also tells for a particular gain, your roots are purely imaginary. For a particular gain, your roots are purely imaginary, and at that particular gain, our system is obviously undamped in nature. So because undamped is because from the time domain analysis, we knew that for undamped nature, the roots were pure imaginary. Okay, so the story goes like that. If you have a purely imaginary roots, the system is undamped, or at the point of intersection on the imaginary axis in a root locus, the roots are purely imaginary, therefore at that particular gain system is undamped. And here also the meaning is same, S equal to J omega is made assuming the system is undamped, but parallelly we are interpreting that substituting S equal to J omega tells us that there exist continuous oscillations, undamped oscillations at the output. So we are trying to visualize or correlate the sinusoidal output as undamped output. That is the only thing we are doing here. Since our output is always continuous because of a sinusoidal input, the output we get as a sinusoidal output. This sinusoidal output is assumed to be undamped in nature, and therefore no harm in substituting S equal to J omega in our second order system. So we write omega n square, J omega square plus 2 zeta omega n, S is J omega into omega n square as it is. So here I make a small modification for the above expression. I will divide both numerator and denominator by omega n square. Divide both numerator and denominator by omega n square. So omega n square and omega n square cancel. Omega by omega n square is like this. And the second term here, we have omega by omega n. One omega n will cancel. And I forgot to write zeta here. So zeta, yeah, zeta should be written like this. So I will call u equal to omega by omega n. Okay, so I will make a replacement for omega by omega n. So what we have at the end is 1 by 1 plus 2 zeta u or 2u zeta and j as it is minus omega by omega n square whole square as u square. So now this modification give me real and imaginary terms in the denominator. So I repeat, this substitution of s of j omega is to make the system look like an undamped system, but which is actually not undamped. So now we can separate out magnitude. So in the denominator, take real terms and imaginary terms separately. So 2 zeta u whole square, 1 minus u square whole square. This is magnitude. Now phase angle. Phase angle is a very important one. Okay, so phase angle has a condition here. denominator, we can write tan inverse of 2 zeta u, the imaginary term, divided by the real term, 1 minus u square. So this expression is valid only when 1 minus u square is positive. Okay, only when 1 minus u square is positive, which means the real part is lying in the real axis. Okay, and imaginary is assumed to be positive because 2 zeta u. Now, what is the scenario if u is greater than 1? So, if u is greater than, obviously the real value is negative. So, when real value is negative, it lies on the 180-degree line. So, our phase angle now is 180 minus tan inverse of 2 zeta u divided by, either you can write u square minus 1 or take only the magnitude by writing 1 minus u square. Both are fine. Both are fine. So these are our expressions for magnitude. This is for magnitude and this is for phase angle. So phase angle has two cases. U less than 1 is one scenario and u greater than is one another scenario. So this term is only magnitude is considered. So what we did is only the mathematical derivation. You need to correlate these things practically. Okay. So first what I have shown, I considered a system, I applied an input signal of a particular frequency, then we took a output for that particular frequency, we plotted on gain plot as well as phase plot, then we went on joining all those points, then we got some curve on the graph. So that is actually the frequency response of that particular system. Then we need to extract some key features from those graphs. So those key features, you should be able to get it theoretically also. So just similar to time domain specification, we derived theoretically the expression for TR, TS, TP, okay, everything from the second order system. So similarly here, we need to derive the expression for omega r resonant frequency and peak resonant, and we are supporting that graphical value with a theoretical derivation. Fine. Any queries? Anybody has any queries? Okay, then if you have no queries, I will end the lecture. Please go through this explanation once again, and especially the PPTs. I will share this PPT with Ganesh, and if you try to correlate the concept of signals with the controls, that will be very much advantageous, I can say. I'll just try to show that RC analysis is done here. Yeah, this is how the theoretical expressions can be used. This is how the graph looks like. Fine. So thank you one and all. We'll continue with this in the next class.